What is it about generative AI models, specifically foundation models, that is reshaping industries across the globe? This is a question that is well answered in this course, which brings into focus the core principles of generative AI. These principles are at the heart of creating powerful AI models, platforms, and applications that can solve complex, real-world problems relatively quickly. With a strong understanding of these principles, you can maximize your experience of generative AI. Therefore, this course invites all beginners, whether professionals, enthusiasts, practitioners, or students. If you have a genuine interest in the rapidly developing field of generative AI, this course is for you. A course for everyone, regardless of your background or experience. By the end of this course, you'll be able to identify the core concepts that form the building blocks of generative AI, list the capabilities of commonly used generative AI models, explain how foundation models generate text, images, and code, and describe the purpose of dynamic AI platforms, such as IBM Watsonx and Hugging Face. As this is a focused course comprising 3 modules, you're expected to spend 1 to 2 hours to complete each module. In Module 1 of the course, you'll explore the principles and components of deep learning architecture and understand how large language models are created. You'll also differentiate between the capabilities of commonly used generative AI models, such as variational autoencoders, generative adversarial networks, transformer-based models, diffusion models, and foundation models. In Module 2, you'll learn how pre-trained foundation models generate text, images, and code through examples of T5, the bidirectional autoregressive transformer model, Imagen, and code-to-sequence models. Further, in this module, you'll understand how dynamic AI platforms such as IBM Watsonx and Hugging Face are helping businesses create value and gain a competitive edge. Module 3 requests your participation in a final project and presents a graded quiz to test your understanding of course concepts. You can also visit the course glossary and receive guidance on the next steps in your learning journey. The course is curated with a mix of concept videos and supporting readings. Watch all the videos to capture the full potential of the learning material. You'll enjoy hands-on labs that demonstrate the capabilities of foundation models and participate in a final project in Module 3. There are practice quizzes at the end of each lesson to help you reinforce your learning. At the end of the course, you'll also attempt a graded quiz. The course also offers discussion forums to connect with the course staff and interact with your peers. Most interestingly, through the expert viewpoint videos, you'll hear experienced practitioners share their perspectives on the concepts covered in the course. If you've been wanting to get a grasp on the technology that's pushing the boundaries of machine learning, you've come to the right place. Let's get started. Welcome to Deep Learning and Large Language Models. After watching this video, you'll be able to explain the core concepts of generative AI, such as deep learning, and describe how large language models can perform human-like tasks. How does deep learning occur? Depth is created with layers. The more layers of information you process, the deeper your understanding of life around you. This is how the human brain works. And this is the driving principle behind deep learning techniques. An artificial neural network, or ANN, makes deep learning possible. ANNs comprise several computing units called neurons, which are organized in 3 connected layers: the input layer, one or many hidden layers, and the output layer. When a vast data set is introduced to the network, the neurons in the input layer capture the data. The neurons in the hidden layers then study the data. Each neuron in the hidden layer contains inherent bias parameters. The connection between 2 neurons establishes weight parameters. Parameters can be defined as internal values of a network that get optimized as neurons repeatedly train on vast data sets. The higher the number of bias and weight parameters, the stronger is the computational power of the network, which leads to increased predictive accuracy. Sometimes, deep learning algorithms are trained on supervised or labeled data sets where each input data point has a known output. Such supervised learning helps create tools that filter emails, check credit scores, detect fraud, and enable image and voice recognition systems. While better labeling can lead to better quality trained algorithms, it introduces some constraints. Supervised learning algorithms are restricted to deliver a predefined response, and labeled data is time-consuming and costly to obtain. More often than not, deep learning algorithms are trained on unsupervised or unlabeled data, where the training data consists of input data without explicit target outputs. Clustering and dimensionality reduction are common applications of unsupervised learning. In clustering, the algorithms group similar instances together based on their inherent properties, whereas in dimensionality reduction, the algorithms capture the most important features of the data while discarding redundant or less informative ones. Therefore, unsupervised learning algorithms are freer to discover patterns and hierarchies within the dataset, thereby producing more efficient, accurate results. This is why a deep learning algorithm's ability to produce high-quality responses largely depends on the quality of the vast dataset they are asked to explore and query. There is one other factor that can also differentiate the level of responses produced by deep learning algorithms. The neural network architecture deployed in deep learning influences the responses produced by algorithms. There are 3 types of deep learning architectures that are discriminatingly used: convolutional neural networks, or CNNs, recurrent neural networks, or RNNs, and transformer-based models. Convolutional neural networks contain a series of layers, each of which conducts a convolution or mathematical operation on a previous layer. When applied to grid-based data such as images, CNNs can quickly extract useful information from images to recognize patterns, classify images, and segment pictures. CNNs are useful in image processing, video recognition, and natural language processing. In contrast, recurrent neural networks are more efficient at processing sequential data, such as text or speech. They possess a memory component that enables them to capture dependencies and contextual information over time. RNNs are useful in machine translation, sentiment analysis, and speech recognition. Transformer-based models do not use convolutions or recurrence to process data. Instead, they have a 2-stack structure where an encoder and decoder process an exceptionally high number of parameters to understand language patterns at a greater depth. The deep learning algorithms in a transformer can analyze and capture the context and meaning of words in a hierarchical sequence and predict the next word in the output sequence. The result is the creation of a large language model that can perform natural language processing, or NLP, tasks, such as content generation, predictive analysis, language translation, and process automation. These large language models, or LLMs, form the base mechanism for generative AI applications. Examples of LLMs include OpenAI's generative pre-trained transformers GPT-3 and GPT-4, Google's PaLM 2, and Meta's Llama. For instance, GPT-4 is a language processing AI trained on a massive corpus of text data from the internet, including books, articles, and websites. The model has over 170 trillion parameters. This helps it perform natural language processing tasks such as creating content, setting up dialogue systems, and translating languages. People leverage these capabilities to write high-caliber essays and case papers, or perform machine translation and summarization. Organizations use these capabilities to power chatbots and virtual agents, and even translate international business communication or their web content into local languages. As deep learning architecture and technology evolves, LLMs will also deliberate harder to deliver more accurate and acceptable outcomes, helping generative AI models perform increasingly complex tasks. In this video, you learned about the core concepts of generative AI and understood how large language models perform human-like tasks. LLMs leverage the power of transformer networks to pre-train deep learning algorithms on vast datasets. These algorithms capture patterns and hierarchies within datasets to generate accurate human-like responses. This technology makes generative AI scalable. Welcome to Generative AI Models. After watching this video, you'll be able to identify the core generative AI models that serve as the building blocks of generative AI and list their distinctive features. In the world of generative AI, these 4 models have made a significant impact: variational autoencoders, generative adversarial networks, transformer-based models, and diffusion models. Each model employs a different type of deep learning architecture and applies probabilistic techniques. Let's gain insight into how they work. Variational autoencoders, or VAEs, are the most popular of all generative AI models for 2 reasons. A, they work with a diverse range of training data, such as images, text, and audio, and B, they rapidly reduce the dimensionality of your image, text, or audio to create a newer, improved version. First, the encoder, which is a self-sufficient neural network, studies the probability distribution of the input data. In simple terms, this means that it isolates the most useful data variables. This allows the encoder to create a compressed representation of the data sample and store it in the latent space. You can think of this latent space as a mathematical space within the model's architecture, where large dimensional data is represented in a compressed format. Next, the decoder or reverse encoder, which is also a self-sufficient neural network, decompresses the compressed representation in the latent space to generate the desired output. Basically, the algorithms are trained using a maximum likelihood principle, which means they try to minimize the difference between the original input data and the reconstructed output. Although VAEs are trained in a static environment, their latent space is characterized as continuous. Therefore, they can generate new samples by randomly sampling from the probability distribution of data. Because they can produce realistic and varied images with little training data, VAEs are used in image synthesis, data compression, and anomaly detection tasks. For example, the entertainment industry uses VAEs to create game maps and anime avatars. The finance industry uses VAEs to forecast the volatility surfaces of stocks. The healthcare sector uses VAEs to detect diseases using electrocardiogram signals. Generative Adversarial Network, or GAN, is another type of generative AI model that uses imagery and textual input data. In this model, two convolutional neural networks, or CNNs, compete with each other in an adversarial game. One CNN plays the role of a generator and is trained on a vast data set to produce data samples. The other CNN plays the role of a discriminator and tries to distinguish between real and fake samples. Based on the discriminator's responses, the generator seeks to produce more realistic data samples. GANs can generate new realistic-looking images, perform a style transfer or image-to-image translation, and even create deepfakes. The finance industry uses GANs to train models for loan pricing or generating time series. Tools such as SpaceGAN work with geospatial data, and NVIDIA's StyleGAN2 is known for creating video game characters. Unlike variational autoencoders, GANs can be challenging to train as they require a large amount of data and heavy computational power. They can potentially create false material, which is an ethical concern. Transformer-based models were introduced a few years ago, when recurrent neural networks, or RNNs, started facing a problem called vanishing gradients. Due to this problem, RNNs were struggling to process long sequences of text. To get around this challenge, transformers were built with attention mechanisms that could focus on the most valuable parts of the text while filtering out the unnecessary elements. This allowed transformers to model long-term dependencies in text. For instance, when you enter a simple prompt, the two-stack transformer architecture uses an encoder-decoder mechanism to generate coherent and contextually relevant text. As transformer models can query extensive databases, they are able to create large language models and perform natural language processing tasks, such as picture creation, music synthesis, and even video synthesis. This marks a significant breakthrough in our approach to content creation and offers many opportunities for innovation, as has been seen with GPT 3.5 and its subsequent versions, BERT and T5. Diffusion models are a more recent addition to the world of generative AI models. They address the systematic decay of data that occurs due to noise in the latent space. By applying the principles of diffusion, these models try to prevent information loss. Just as in the diffusion process where molecules move from high-density to low-density areas, diffusion models move noise to and from a data sample using a two-step process. Step 1 is forward diffusion, in which algorithms gradually add random noise to training data. Step 2 is reverse diffusion, in which algorithms turn the noise around to recover the data and generate the desired output. OpenAI's DALL-E 2, Stability AI's Stable Diffusion XL, and Google's Imagen are mature diffusion models that generate high-quality graphical content. Similar to variational autoencoders, diffusion models also try to optimize data by first projecting it onto the latent space and then recovering it back to the initial state. However, a diffusion model is trained using a dynamic flow and therefore takes longer to train. Then, why are these models considered the best option for creating generative AI models? because they train hundreds, maybe even an unlimited number of layers, and have shown remarkable results in image synthesis and video generation. Experiments with generative AI models continue unabated as unsupervised algorithms throw up one surprise after another. In this video, you learned about the 4 core generative AI models that serve as the building blocks of generative AI. Variational autoencoders rapidly reduce the dimensionality of samples. Generative adversarial networks use competing networks to produce realistic samples. Transformer-based models use attention mechanisms to model long-term text dependencies. Diffusion models address information decay by removing noise in the latent space. Welcome to Foundation Models. After watching this video, you'll be able to define the term foundation model, explain key characteristics of foundation models, identify the capabilities of foundation models, and explore examples of foundation models. Stanford University Center for Research on Foundation Models defines a foundation model as a new successful paradigm for building AI systems. Train one model on a huge amount of data and adapt it to many applications. We call such a model a foundation model. Let's explore this definition more closely. The first part of this definition says, train one model on a huge amount of data. How does this work? A foundation model is a large general-purpose self-supervised model that is pre-trained on vast amounts of unlabeled data, establishing billions of parameters. Pre-training is a technique during which unsupervised algorithms are repeatedly given the liberty to make connections between diverse pieces of information. This allows foundation models to develop multimodal, multi-domain capabilities such that they can accept input prompts in multiple modalities such as text, image, audio, or video formats, and perform complex and creative tasks such as answering questions, summarizing documents, writing essays, solving equations, extracting information from images, even developing code. This broad skill set makes these models relevant to multiple domains. This is in contrast to smaller generative AI models, which are trained on restricted domain data and requested to perform limited tasks. For instance, OpenAI's DALL-E family of models are considered foundation models because they can perform many image-related tasks. In contrast, AlexNet is not classified as a foundational model, as it only performs image classification tasks. Therefore, we can clarify that while all foundation models have generative AI capabilities, not all generative AI models are foundation models. When foundation models are trained on vast natural language processing databases, they are called large language models, or LLMs. LLMs develop independent reasoning, allowing them to respond to queries uniquely. For example, OpenAI's GPT-N class of models, including GPT-3, which is pre-trained on 175+ billion parameters, and GPT-4, which is pre-trained on an estimated 180+ trillion parameters. Other examples of large language models include Google's Pathway language model, pre-trained on 540 billion parameters. Meta's large language model, Meta AI, pre-trained on 65 billion parameters. Google's BERT, pre-trained on 340 million plus parameters. Meta's Galactica, an LLM for scientists, pre-trained on 48 million papers, lectures, textbooks, and websites. Technology Innovation Institute's Falcon 7B, pre-trained on 1.5 trillion tokens. And Microsoft's Orca, pre-trained on 13 billion parameters and small enough to run off a laptop. It's likely that these parameters may change as generative AI tools evolve in their scope and size. Another aspect of models evolving is their ability to adapt. The definition also suggests that we can adapt a foundation model to many applications. This is possible because of the broad-based training of foundation models, which allows them to learn new things and adapt to new situations. Small businesses can leverage this capability to create customized, more efficient generative AI models at an affordable cost. This is why foundation models are also called base models. They help make AI systems more accessible to businesses and individuals who do not have the resources to train their models from scratch. In this way, foundation models enable enterprises to shrink time to value from months to weeks. Take, for example, the evolution of chatbots. OpenAI's GPT-3 and GPT-4 are foundation models that power the ChatGPT chatbot. Google's Palm powers the Google Bard chatbot. These are today's unreasonably clever chatbots. However, if we think back to how early chatbots functioned, we realize that they were trained on smaller datasets, which confine their generative capabilities. While they could predict responses based on keywords, they could only provide a predetermined response. In contrast, chatbots today are pre-trained multiple times on extensive data sets. They are therefore able to increase their word prediction accuracy and respond in a more helpful and creative manner. Try this, will you? If you type a single sentence prompt in ChatGPT, you'll likely get more than a basic response. Depending on what your prompt requested, the chatbot may write a comparative essay, create an infographic, design a checklist, or script a short story. OpenAI's GPT-3 is also the foundation model for DALL-E, an image generation tool that responds to text prompts. For a single text prompt, DALL-E generates 4 high-resolution images in multiple styles, including photorealistic images and paintings. Another clarification to note here. While all large language models are foundation models, not all foundation models are large language models. Some foundation models use diffusion architecture capabilities to improve the scale and scope of their image generation capabilities. For instance, DALL-E uses transformer architecture, but the latest version of DALL-E uses sound diffusion to generate images from text. Stability AI's Stable Diffusion uses diffusion architecture to generate high-resolution images in realistic, cartoony, and abstract styles based on the user's description. Google's Imagen uses a cascaded diffusion model built on an LLM to generate images from text prompts. As foundation models evolve in their strengths and applications, we have seen some limitations. Firstly, the desired output may be biased if the data on which the foundation model is trained is biased. Secondly, LLMs can hallucinate responses. That means they generate false information because they misinterpret the context of data parameters within a data set. Therefore, you must verify the accuracy of the output produced by a generative AI chatbot. With a little caution, you can enjoy the many benefits foundation models offer. In this video, you explored the concepts of foundation models. These models are pre-trained on billions of parameters, which allows them to develop independent reasoning and execute a large variety of complex tasks. Given their multimodal, multi-domain capabilities, they can serve as the foundation or base for generative AI applications. Welcome to Pre-trained Models, Text-to-Text Generation. After watching this video, you'll be able to explore the different models used for text-to-text generation in generative AI. You'll also be able to describe the uses and benefits of these models. Summarize, code, translate, create content. These are just some of the things that text-to-text generation models can do for you. But what exactly are text-to-text generation models? Text-to-text generation models are a type of machine learning model used to generate text from a given input. They are trained on a large corpus of text. These language models are trained to learn patterns, grammar, and casual information. Using this input, the models generate the new text and can generate a variety of text formats, including code, scripts, musical pieces, emails, letters, and so on. There are 2 main text-to-text generation models: statistical and neural network models. Statistical models use statistical techniques to generate text. One common statistical model is the Markov chain. A Markov chain generates text by starting with a seed state and then generating the next state based on the previous state. For example, it can predict and generate the next character based on previously observed language patterns. Markov chains can generate text for several purposes, like speech recognition and journalism. Neural network models use artificial neural networks to generate text. These models can represent complex relationships between data. Neural network models are typically trained on a large text corpus. They can then generate text similar to the text they were trained on. Text-to-text generation models use either sequence-to-sequence or transformer type of models. Sequence-to-sequence models first encode the input text into a sequence of numbers, then decode this sequence into a new one, representing the generated text. Some examples of these tasks are summarization, speech recognition, and machine translation. Transformer models directly map the input text to the generated text, allowing the models to generate more fluent and natural-sounding text than sequence-to-sequence models. A key feature of transformer models is how they leverage an AI concept called attention to emphasize the weight of related words. This can help provide the context for a specific word or token describing some other type of data, for example, a section of an image. Let's explore some of the most popular text-to-text generation models. First, you have the GPT created by OpenAI. It is a substantial language model. Its development involved training on an extensive corpus of text and code, equipping it with the capability to produce text, perform language translation, generate diverse forms of creative content, and provide informative responses to user inquiries. Then there is T5. T5 is a text-to-text transfer transformer model developed by Google AI. This model is also trained on a substantial dataset of code and text. It can be used for various tasks, including summarization, translation, and question answering. What makes T5 popular? Generating text requires capabilities accomplished using deep learning models based on natural language processing, also called NLP. However, you need one model for language translation and another for language auto-completion, making the approach inefficient. It gives rise to the need for a unified model capable of producing coherent and contextually appropriate text. This requires an architecture that can convert all input and output data into text. The model can then learn from diverse examples and apply the learning to a wide range of tasks in NLP. T5 is the answer to this need. It is a universal model that uses a standard encoder-decoder architecture to perform various tasks like transformations and classifications. It also leverages transfer learning capabilities. The model trained on the data for one task can be fine-tuned to perform another downstream task in the same domain. Finally, you have BART. BART is a bidirectional auto-regressive transformer model developed by Facebook AI. BART is a deep neural network with a sequence-to-sequence translation architecture with bidirectional encoder representation like BERT and a left-to-right decoder like GPT. BERT stands for bidirectional encoder representations from transformers. It refers to a family of language models by Google that uses pre-training and fine-tuning to create models that can accomplish several tasks. BART's bidirectional nature processes text forward and backward. This BERT and GPT decoder combination allows BART to perform tasks like analyzing sentiment, answering questions, NLP tasks like language translation, and generating human-like text. Further, its auto-regression nature allows it to generate contextual text, taking feedback from previously generated tokens to generate new ones. The BART capability also applies to computer vision tasks. The versatility of the model makes it useful across industries. I'm sure by now you can see how text-to-text generation models can be powerful tools for task completion. Let's look at some examples. There is text summarization, where these models can process the input text to generate the summarized text without changing the original text's meaning. Text-to-text models can support conversational intelligence by providing personalized assistance through text-based query responses. Finally, did you know that text-to-text models can produce digital text that helps create product descriptions, write emails, create resumes, and so on? Now that's something. Because of these versatile applications, text-to-text models offer several benefits. They increase productivity through automation. For example, they can generate marketing copies or even create social media posts. They improve the accuracy of tasks prone to human error. For example, a text-to-text generation model can translate documents in context without mistakes. In this video, you learned the meaning of text-to-text generation models in generative AI. You learned the two types of text-to-text generation models, statistical and neural networks. Text-to-text generation models use either sequence-to-sequence or transformer type of models. You also explored the most popular text-to-text generation models, GPT, T5, and BART. Finally, you learned the several uses and benefits of these models. Welcome to Pre-Trained Models, Text-to-Image Generation. After watching this video, you'll be able to explore the different models used for text-to-image generation in generative AI. You will also be able to describe the uses and benefits of these models. Text-to-image generation models are a type of machine learning model. They are used to generate images from text descriptions. They use generative AI to make meaning out of your words and turn them into unique images. Text-to-image generation models are trained on a large dataset of text and images and can be used to generate various types of images. These can be realistic images, abstract images, or even images that do not exist in the real world. There are two types of text-to-image generation models: generative adversarial networks, also called GANs, and diffusion models. Let's look at each. GANs are a type of machine learning model that can be used to generate realistic images. They work by training two models against each other: a generator model that generates images and a discriminator model that distinguishes between real and fake images. The generator model is gradually improved over time until it can generate images that are indistinguishable from real images. Diffusion models are also a type of machine learning model. They are used to generate images from text descriptions. They work by starting with a random image and gradually adding detail to the image until it matches the text description. Diffusion models are typically more efficient than GANs and can be used to generate more creative and abstract images. Let's explore the most popular text-to-image generation diffusion models, DALL-E and Imagen. DALL-E is a text-to-image generation model developed by OpenAI. DALL-E is trained on a massive dataset of text and images and can be used to generate realistic images from various text descriptions. It also incorporates an evaluation mechanism to determine whether the final picture is accurate. To achieve this, DALL-E uses a combination of its core elements: natural language processing, also known as NLP, machine learning, and computer vision. For example, it can take a simple description, like a panda juggling a ball, and turn it into a photorealistic image that hasn't been created before. Not only that, but DALL-E can also edit photographs based on a simple text description, such that the edit blends in seamlessly with the original image. It's called inpainting. DALL-E is special because deep learning allows it to understand individual objects such as pandas and balls and how things are related. The latest version of DALL-E is a large model, but not nearly as large as GPT-3, and interestingly, smaller than its predecessor. Despite its size, this newer version generates 4 times better resolution images than the former version of DALL-E. So what are the benefits of DALL-E? An image generated by DALL-E tells us if the system understands what we've communicated or merely repeats what it has been taught. Further, DALL-E plays a crucial role in developing useful and safe AI by enabling us to understand how AI makes sense of our world. The second popular model is Imagen. Imagen is a text-to-image generation model developed by Google AI. Just like DALL-E, Imagen is also trained on a massive data set of text and images. Imagen is used to generate realistic images from a wide variety of text descriptions. Imagen leverages the power of large transformer models and deep language understanding to generate high-fidelity images. An important discovery has been that large language models like T5 pre-trained on text are pretty effective at encoding text to generate images. Hence, it would follow that increasing the language model size in Imagen would also augment image fidelity rather than increasing the size of the image diffusion model. Imagen claims to be able to produce an unprecedented degree of photorealism, which is one of its key advantages. This is how it works. The model picks up text, such as 2 white umbrellas rising into the sky. Clouds are moving. It is raining, and converts it into an image depicting just that. The image could be either photorealistic or an artistic interpretation. In this video, you learned how text-to-image generation models work. These models are classified into 2 types, GANs and diffusion models. Within diffusion models, you explored the most popular text-to-image generation models, DALL-E and Imagen. Finally, you learned the benefits of each of these models. Welcome to Pre-Trained Models, Text-to-Code Generation. After watching this video, you'll be able to explain how text-to-code generation models work in generative AI. You'll also be able to identify the different text-to-code models and describe their uses and benefits. Text-to-code generation models are a type of machine learning model used to generate code from natural language descriptions. The models use generative AI to write code through neural code generation. Neural code generation is a process that uses artificial neural networks loosely based on neural networks in the human brain. These neural networks are trained on a substantial data set of code examples and then fine-tuned to generate code snippets, functions, and complete applications. The generated code is similar in structure and function to the examples it has been trained on. There are 2 main text-to-code generation models, sequence-to-sequence and transformer. Sequence-to-sequence models are a type of machine learning model that can translate from one domain to another. In the case of text-to-code generation, the model can translate natural language descriptions into a code sequence. Transformer models are also a type of machine learning model that can learn long-range dependencies between words. In the case of text-to-code generation, the model is trained to understand the relationships between the words in a natural language description and the corresponding code. Several popular text-to-code generation models exist within the sequence-to-sequence and transformer model classifications. Let's look at some of them. The first model is Code T5, a sequence-to-sequence model developed by Google AI. Code T5 is the first pre-trained programming language model that is code-aware and encoder-decoder based. Like most models, Code T5 is trained on a large dataset of text and code. It can enable a wide range of code intelligence applications. These include code understanding and generation tasks. Some examples of these tasks are text summarization, question answering, and language translation. The second popular model is Code to Sequence. Code to Sequence is a sequence-to-sequence model developed by OpenAI. It is an alternative approach that leverages the syntactic structure of programming languages to encode source code even better. Having been trained on a substantial text and code dataset, Code to Sequence can generate code for several tasks, such as code summarization, documentation, and retrieval. For example, the Code to Sequence approach can caption code snippets. That is, it can assign a natural language caption to the task performed by the snippet. Finally, you have the PanGoo coder. PanGoo coder is a transformer model developed by Microsoft Research. PanGoo coder is a pre-trained decoder-only language model that generates code from natural language descriptions. It's built on the PanGoo Alpha architecture, a large-scale neural network used for natural language processing, also called NLP. This model can generate code for tasks like function definition, class definition, and program synthesis. For example, PanGoo coder can successfully synthesize running code to solve a problem based on a natural language description. In addition, several other general-purpose foundation models can be used for text-to-code generation, such as OpenAI's GPT and Code Llama by Meta. GPT excels in human-like text generation and demonstrates impressive capabilities in code creation. Code Llama can generate and explain code in natural language, specifically English. Similarly, some universal generative AI tools for text-to-code generation are GitHub Copilot and IBM Watson Code Assistant. GitHub Copilot, powered by OpenAI Codex, can generate code based on various programming languages and frameworks. IBM Watson Code Assistant is built on IBM Watsonx.ai and enables developers to write code accurately and efficiently with real-time recommendations, autocomplete features, and code restructuring assistance. There are several uses and benefits of text-to-code generation models and tools. Let's look at some of them. Text-to-code generation plays a crucial role in auto-completion, helping developers by suggesting and completing code snippets or statements as they type. For example, as a developer types a code comment in Python or any programming language, auto-completion suggests relevant keywords, variable names, or function names based on the context of the comment. This helps the developer quickly reference and document parts of the code, improving code documentation and readability. Text-to-code generation models can automatically generate code based on natural language descriptions. Here's an example to illustrate how. The task is generating Python code from natural language description. The natural language description is create a Python function that can calculate the factorial of a given integer. Here, you can see the generated Python code. Furthermore, the stable underlying architecture of text-to-code generation tools reduces the time spent on debugging. Debugging is when errors in software programs and systems are identified and fixed. For example, suppose a developer working on a chatbot using a generative AI model encounters a problem where the chatbot generates irrelevant responses to user queries. The developer states, the chatbot gives irrelevant responses to user queries. I need to fine-tune the model. The text-to-code generation model generates the code snippet shown here. In this case, the text-to-code generation model suggests a code snippet for fine-tuning the chatbot model using user feedback data. This snippet assists the developer in quickly addressing the issue of irrelevant responses and improving the chatbot's performance. That's not all. Text-to-code generation models can also facilitate code translation by automatically translating code between different programming languages, facilitating cross-platform compatibility and migration. They assist with code refactoring and application modernization by automating the identification of outdated or inefficient code segments and suggesting optimized replacements, streamlining the modernization process. Text-to-code generation models can even provide recommendations for libraries and frameworks based on project requirements, helping developers make informed choices. Text-to-code generation models can generate test data by automatically creating code snippets that populate databases or data structures with diverse and realistic test cases, saving time in the testing process. Finally, text-to-code models can automatically generate code documentation by generating comments, function descriptions, and documentation based on code functionality, making code bases more understandable and maintainable. In this video, you explored the various text-to-code generation models and learned how they work. There are two types of text-to-code generation models: sequence-to-sequence and transformer. You also learned about the most popular text-to-code generation models: Code T5, Code-to-Sequence, and PanGooCoder and their uses. Finally, you learned the various uses and benefits of text-to-code generation models and tools for auto-completion, debugging, code translation, code refactoring, and application modernization, providing recommendations for libraries and frameworks, test data generation, and code documentation. Welcome to IBM Watsonx.ai. After watching this video, you'll be able to explain the capabilities and features of IBM Watsonx.ai and identify the common tools available in Watsonx.ai. Generating poem, art, or a song through AI is fun, but when AI is applied to business, you need to think bigger. AI for businesses need to be built based on requirements based on higher standards. When you build AI in the core of your business, it needs to be trusted, secured, scalable, and adaptable. Here is a platform that helps businesses leverage AI: IBM Watsonx. IBM Watsonx is an integrated AI and data platform for AI builders. The Watsonx platform comprises three products. The first product is Watsonx.ai, a studio for new foundation models, generative AI, and machine learning. The second product is Watsonx.data, which is a data store. And the third product is Watsonx.governance, which is a toolkit for monitoring and governance. In this video, we'll focus on Watsonx.ai. Watsonx.ai is a studio of integrated tools powered by foundation models for working with generative AI and building machine learning models. With Watsonx.ai, you can train, tune, deploy, and manage foundation models easily. This helps you build AI applications in a fraction of the time and with a fraction of the data. With Watsonx.ai, these are some prominent goals you can achieve: build machine learning models, experiment with foundation models, and manage the AI lifecycle. Based on your goal, you can select the tasks offered by Watsonx.ai. These tasks can be performed using the tools provided on the platform. The tasks and tools in Watsonx.ai align with the AI lifecycle of a model. You prepare your data, build an experiment, and train models and solutions. Then you deploy your models and start building your applications. Subsequently, you manage these models and repetitive processes. Watsonx.ai offers access to IBM's selected open source models from Hugging Face, as well as a family of IBM-trained foundation models of different sizes and architectures. As an AI value creator, you can also bring your models and data to Watsonx.ai. With tools like PromptLab, AI builders can experiment with foundation models and build prompts that meet their needs. PromptLab enables users to experiment with prompts to support a range of natural language processing, or NLP tasks, including question answering, content generation and summarization, text classification, and extraction. As an AI creator, you may also want to customize models based on your data and for your business use cases. Watsonx.ai enables you to do so using the Tuning Studio tool. With this tool, subsequent versions of Watsonx.ai will include tuning methods and examples for prompt tuning and fine-tuning foundation models for better performance and accuracy. Putting a model into a product is a multi-step process. For managing and automating a model lifecycle, Watsonx.ai provides the pipeline tool. The pipeline tool can be used to automate the steps involved in loading data, training models, deploying models, and evaluating models. This can reduce the time to get a model into production and improve the accuracy and reliability of models. Let's learn from this video from IBM how different tools in Watsonx.ai help to create a collaborative environment to streamline workflow for AI models.
Until recently, AI models had to be trained to perform a very specific task. But now, with the power of foundation models, you can build powerful AI applications in a fraction of the time with a fraction of the data. In our prompt laboratory, you can guide models to meet your needs with easy-to-use tools for building and refining performant prompts to achieve your desired result. If you want to further customize, you can tailor models to be even more accurate for your business's use case. In our Tuning Studio, bring in data sets and tune your model with as few as 100 examples. We provide state-of-the-art tuning methods that you can set up with just a few clicks. Now it's time to put your model to work. Create an enterprise-grade deployment and start building your application. That's it. With Watsonx.ai, your team is empowered by a collaborative environment that streamlines workflows throughout the AI lifecycle. Multiply the power of AI for your enterprise. Practical, efficient, and easy to use. Watsonx.ai.
IBM Watsonx.ai ensures the security of the data and models you work on. Your data and the models you create are accessible only to you. Your data is stored in an encrypted format. The models that you create are also private to your account. IBM does not have access to your data or models, and they will never be used by IBM or any other person or organization without your permission. In this video, you learned about IBM Watsonx, an AI and data platform that helps businesses create AI responsibly and with transparency. One of the products of Watsonx is Watsonx.ai. Watsonx.ai is a studio of integrated tools to train, tune, and deploy generative AI models. Prominent tools offered in Watsonx.ai include Prompt Lab, Tuning Studio, and Pipeline Tool. Welcome to Hugging Face. After watching this video, you'll be able to explain the purpose of the Hugging Face platform, list the tools and capabilities it offers, and understand how Hugging Face and Watsonx.ai jointly help businesses. Hugging Face is an open-source artificial intelligence platform where scientists, developers, and businesses collaborate to build personalized machine learning tools. The platform was built with the purpose of creating a hub for the open-source AI community to share models, datasets, and applications. This way, AI becomes accessible to all types of users, even those who do not have the budget or bandwidth to build machine learning applications independently. Hugging Face is, therefore, credited with democratizing AI as everyone comes together to benefit from smaller, curated models, challenging the general one-model-to-rule assumption. At first, the Hugging Face community focused on creating transformer-based models to leverage the capabilities of natural language processing, or NLP. However, today, the platform offers various machine learning tools for generating text, images, audio, and video. Currently, the Hugging Face platform hosts over 250,000 open models, 50,000 datasets, and 1 million open demos. This list keeps growing. Scientists and developers use Hugging Face to build, train, and deploy their AI models. They have access to the platform's open-source transformer library, which has over 25,000 pre-trained models for PyTorch, TensorFlow, and Google JAX. PyTorch is a deep learning library, TensorFlow is a machine learning platform, and Google JAX is a machine learning framework. The models in the library perform varied tasks such as text generation, question answering, summarization, automatic speech recognition, and image segmentation, just to name a few. Users can filter these models by name to find an existing model or share their own model with the library. Developers can also host demos of generative AI applications on the Spaces tab, allowing users to interact and validate them. How do businesses benefit from the platform? Hugging Face offers businesses the enterprise hub from where they can access pre-trained models and datasets. This allows businesses to leverage existing infrastructure rather than build models from scratch. Not only does this reduce their carbon footprint, time, and cost to scale, it also allows businesses to train the models on proprietary data and relevant use cases. Additionally, Hugging Face helps businesses A. add or remove features to improve the efficiency of their models, B. evaluate their generative AI models to filter biased data, and C. create multimodal applications with text, image, audio, and video generation capabilities. More than 50,000 large and small companies actively use Hugging Face. For example, Writer, a generative AI solution provider, hosts its Palmyra large language models, or LLMs, on Hugging Face. Intel has officially joined Hugging Face's hardware partner program and is collaborating with Hugging Face to build state-of-the-art machine learning hardware and end-to-end machine learning workflows. Even universities and nonprofits are part of Hugging Face. Among other services, Hugging Face offers an expert acceleration program to guide non-developers on machine learning models. Hugging Chat is the first open-source alternative to ChatGPT. To protect its users, Hugging Face complies with Service Organization Control Type 2 regulation. This means ensuring user data security, availability, processing integrity, confidentiality, and privacy. Taking its collaborative efforts one step further, Hugging Face has entered into a unique partnership with Watsonx.ai, IBM's next-generation enterprise studio for AI builders. Watsonx.ai offers select Hugging Face models in its studio to help its community of builders train, test, and deploy all types of machine learning and generative AI applications. This way, the studio leverages the diversity of data, community strength, and open source libraries that Hugging Face provides. On its end, Hugging Face creates open source versions of IBM's LLMs and makes them available on its hub. Both entities believe in open source technology. Both bet on the community to create value in the AI space. As proprietary AI models can quickly become obsolete, Hugging Face may develop an edge over the big five in AI, namely Google, OpenAI, Meta, IBM, and Microsoft. This is because it supports and is supported by the open source AI community that keeps innovating. In this video, you learned all about Hugging Face. This AI platform demonstrates the collaborative power of the open source AI community. It creates space for businesses to build customized proprietary models at a reduced cost in an accelerated timeframe, incurring a lower carbon footprint. Organizations, universities, and nonprofits leverage the platform's tools and services to benefit from natural language processing. In short, you do not have to be a big business to benefit from generative AI.